Okay, so what I want to do is, because the title said all you can eat BFT. So I want to encourage you to, I want to kind of give you at least a glimpse of how a BFT protocol looks like. In particular, I'm going to take kind of, I'm trying to simplify a lot of things and provide kind of a variant of HotStuff, or a simplified HotStuff, to give you a glimpse of how these protocols work, and kind of what are the core ideas in these protocols. So hopefully we'll get to kind of linear communication and talk about responsiveness. Okay, so what do we want to do? So the first thing, as I said, is that we're working in this primary backup world. And in the primary backup world, there's these N replicas. There's an adversary. The adversary is malicious, and this adversary controls F of these replicas. And we're assuming that the number of malicious replicas is less than a third. Why are we assuming that? Because there are lower bounds that show that if there's more than a third, then you're kind of stuck. You can't solve this problem in the partial synchrony model. This is kind of the optimal bound, is to get 3F plus 1. All right, so this is the setting, and we have a primary. This is the primary that receives commands from all the clients, and it's always the problem when the primary is lying. In particular, the thing we want this primary not to do is not to send 2 different messages to 2 different people. So how can we cause this primary not to send 2 different messages to 2 different people? Any suggestions? Yeah, so sorry, that's a good suggestion. Any other? So basically everybody's going to, I'm going to say one thing to one person, one thing to the other person, then everybody kind of exchanges what I said. Any other solution?
Send it all to one person and have it sent.
Sign for one person?
One node and have it sent.
What if that one node is malicious? Yeah. But if you had like a trusted hardware, maybe this trusted hardware could make sure that it only signs one thing. Another example of how you can, you could use that if you trust hardware. Yeah.
Build the protocol or the script language you're using to create only 1 or 2 features, like not to allow people to say too much.
Yeah, that's a good point. So if your protocol, all it wants to do is say one thing, then you can't say 2 different things. So yeah, so you're right. This is like Yeah. So okay, so that's definitely an option. Here, I think we want to be able to at least maybe there are some transactions, and you want to choose. Let's say even in Bitcoin, you can choose how many transactions you put in the block. And the way actually Bitcoin solves this, for example, is that you do the proof of work after you computed the block, right? There's like Bitcoin NG has this idea where you first solve the proof of work and then you can send micro blocks. I don't know if you know this idea, but basically, you can choose these messages after you've been elected. But in Bitcoin, you actually do your proof of work on the block. So you can't generate another hash of a different block. If you have a private key, you can sign 2 different messages. So really the suggestion here is, let's have everybody send to everybody. And what I want to do is kind of suggest a more frugal approach where, we want to get linear communication. So we care about linear communication. So basically, here's the protocol. So the primary sends a message to everybody. So, maybe I send a message to each one of you. And what do? So the first message you hear, you sign it and send it back to me. Okay, so what do? Now I have like a lot of signed messages. Maybe I can combine all these messages together, and I send you back a message. I'll call this, I send a send, you send me an acknowledgement, and I send you back a lock message, and this lock message contains a lot of signatures. Okay, make sense? So if I draw this protocol, so here's the primary. It sends everybody a message. It receives an acknowledgement, and it waits for n minus f to be the same, and it sends this message, this lock message, say to one guy here and to one guy here. So this is a send, and this is an acknowledgement. Right, so the protocol is really simple, right? You're just sending it to everybody. Everybody sends it back to you, and you send this message to everybody. So what have we managed to get? Did we gain anything from doing this protocol? So I want to claim that now an honest replica that receives this lock message has a guarantee that nobody else has a different lock message. Does that make sense? Any reason why? Yeah. Mm-hmm. Yeah, so there is every view, there's a fixed, let's say there's a fixed way to decide who is the primary. That's a great question. Yeah, yeah. Let's say, today you're the primary, right? So you get to say. But we need to make sure that you're not saying two different things. Because if you say two different things, you're going to confuse us. So, you send your message to everybody. Everybody signs back to you. You take enough signatures, which here is n minus f, and then you send that back to everybody.
So, like a schedule with synchronized timestamps?
Yeah. So, there's a content of the message that's x, and then there's v. V is the view number. That makes sense. So, anybody has kind of an idea of why, if I get a message from Roman, it can't be that Omer gets a different message, a different lock message. Maybe. Yeah, so it's not signed by everybody, it's signed by n minus f. So if it's signed by n minus f, how many honest people signed it? At least. N minus 2f, right? So if n minus f signed, then n minus 2f are honest, right? Because at most f malicious. So n minus 2f have signed this message and they're honest, right? So there's n minus 2f that are honest. So how many people, are not in that group? At most 2f, right? If n minus 2f are honest and signed, then the remaining is just 2f. Okay, and 2f is less than n minus f. This is where we needed the 3f plus 1. Okay, so let's kind of say that again with maybe a concrete example. So the concrete example is n equals 4 and f equals 1. Right? This is a concrete example of this protocol. Right? So I'm sending this to 4 members. And how many am I waiting for? For 3. Right? So I'm waiting for 3 responses. And I'm sending 3 signatures to this node here. And so why couldn't this guy get 3 signatures for a different value? Because if this guy got 3 and this guy got 3, how many people are in the intersection? If there's 4 total? At least 2, right? And so if there's 2, that's 1 more than the number of malicious people, right? There's one of them is honest. This one honest node will not send the same, will not send an acknowledgement for 2 different messages. Right? So this is kind of a very simple protocol that we spend linear amount of communication and we make sure that the primary, Roman for today, cannot say 2 different messages, 2 different things. So once we have this primitive, we're going to solve a next problem. And the real problem, and this is kind of the core problem of Byzantine, of distributed computing, is what happens if there is a primary that decides to commit on a command, and then this primary fails. It doesn't even have to be Byzantine. It can just crash. So how do we make sure that once a command is committed, the new primaries will not make a mistake and commit on something else? This is kind of the real core problem of consensus protocols. This happens even in the benign case, even if there's just crash failures. So yeah, how can we do that? How can we make sure that if Roman sends me a command to commit to something, even if he crashes and then we replace the primary with a new one, we still we won't make a mistake? Any suggestions? Yeah, so you need to make sure that a lot of people heard a message. So that's good, but here's the problem. So how does Roman know when to commit? Sorry, how do I know when to? So Roman sends me a message. How do I know that I'm supposed to commit? So I received my message. I don't know if you received yours. Yeah. Yeah, exactly. So you want another round. I mean, so anybody else with any other idea? How can we solve this? So I just kind of want to say that this is okay. Yeah, so one approach is to, if we assume synchrony, it's kind of the Dolev strong approach, is before I commit, I broadcast the message I received to everybody. Right? This is kind of the Dolev strong approach. And this requires synchrony assumptions. The problem could be that we're in partial synchrony, right? So in partial synchrony, it could be that even though I received your message and I commit and I send to everybody, now my messages are being delayed, right? I'm under a denial of service attack, and so nobody's going to see my message. So if you're right, in a synchronous model, that would definitely work. It's done. Yeah. So the way to solve this is if you're using synchrony, you have to broadcast. If you're not using synchrony, then you have to use one more round. And basically, what this round guarantees is that I know that if I committed, then there's enough honest people around here that's going to remember that decision. Maybe they didn't commit, but they will at least remember that decision. And so, the way we do this is doing the same thing that we did earlier. So here's what we start with a primary. So we're basically starting at this point here, and the primary sends a lock message. And you could imagine that instead of committing once you receive a lock message, what we do is we want to gather enough evidence so that when I commit, I know there's enough people that are locked. And that's going to cause safety, right? Because even if I commit and then forget or crash, there's enough people around that will remember my decision. They might not commit yet, but they will remember my decision. So yeah, so what the protocol does is the primary sends a lock to everybody. And if you get a lock, you sign that message, and you send it back to the primary. So you send a acknowledgement for the lock. This is ACK lock. And at this point, the primary again waits for n-f. Why are we waiting only for n-f and not for everybody? By the way. Yeah, so if we want to be able to mask F failures, we can't say we're going to always wait for n replies, right? So if we're waiting for n replies, we might lose liveness. So that's why all these protocols are trying to kind of wait for fewer messages. In particular, n-f is okay because you're saying there's at most f that can be slow or malicious. The rest would eventually their messages will eventually reach. So we wait here, and at this point, we actually can send a commit message. And so when I receive this commit message from the primary, now I can safely know that this event is committed. And why? Because what I hope is that there is enough evidence in the system that the next primary that will come will be able to figure out that this command was committed and not something else. Right? So that's the goal. So in particular, what is the property that happens if I committed? So if I committed, I've seen at least how many locks? In this case, if there's 4, I've seen 3 locks, right? I've seen 3 locks, of which how many of them are from honest participants? At least 2, right? So I received 3 locks. One of them might be from somebody who's malicious, but 2 of them are not malicious. So there's 2 nodes that are locked on this value. So what does that mean? That means when a new primary comes up, he's going to see whether are there values that are locked, right? If there's values that are locked, he's going to use that value that's locked. Now, he can't wait for everybody, so he's going to wait for just 3 out of 4, right? Because this new primary also can't wait for all 4 because then he's going to be stuck. So he waits for only 3 out of 4. But it's still fine. He waits for 3 out of 4. Of the 2, at least one of them will be in that group, right? So I'm guaranteed that at least one of the honest people that sent me a lock message will also be in that group for the new primary that will read this value. And so this is kind of the approach of how we get a safe leader replacement. So again, the commit rule just looks like this. We do this first round. This first round basically makes sure that the primary is sending just one message and not 2 different ones. And then this second round, what it guarantees is that if I did a commit, and there's enough people, enough honest people, that are locked on the value that I committed to. These are the 2 properties that we currently have. And with that, we're now going to replace the primary. And the way we're going to replace the primary is by making sure that if I received a lock message, I'm going to try to only cooperate with primaries that agree with the lock message that I received. Okay, now why is that important? It's important because it could be that I received a lock, but somebody else committed. Right? So I'm actually guaranteeing the safety of the protocol by saying if I have a lock, I'm not willing to work with primaries that suggest something other than what I'm locked on. Make sense? Yeah, so a replica might be locked, and if you're locked on some value, let's say x prime, and you're locked in some previous view. Let's say this was some view, and this primary is locked here. A replica basically keeps in track what is the highest lock that it received. Right. So if it receives a lock in a higher view, it records that highest view lock that it receives. And what is the way that a primary can convince a locked replica to work with a different value? So here's the two things that a primary must do in order to convince a replica to work with a value. The first is if it shows it a higher lock. So in particular, if I'm locked on view 10, and the primary actually says, here's a lock on a higher view, let's say view 12, this is a proof for me as a replica that there was no commit. Right? So if I give a different lock of a different view on a different value, I know there's no commit on the view I'm locked on. That's kind of one approach. I see a higher lock on a different value. And the other is that the primary simply uses the same value I'm locked on. If I'm already locked on x prime, and the primary suggests that, I'm saying, fine, I'm happy with that. So these are the two rules. Otherwise, as a replica, I'm going to ignore the primary. Since I'm locked on a value, and I don't want a malicious primary to kind of force me to work on something else. So in particular, previously the primary just sent the value it wanted to, but now the primary has to check. Maybe it has to repeat the value of the previous leader, because maybe the previous leader committed something, and now the primary has to continue the same thing in order to not break safety. So here's what the primary can do. It can either send the regular value, and this will be accepted by all replicas that are not locked at all, or it can send a value. This is this value y here, and also a previous lock. So this lock is a message that the primary has for the value y for some view w, which is an older view than the current view. So the current view is v, and this is an older view w. So these are the two choices of the primary. So again, previously the naive thing was that the primary could just choose a new value. We said that's not safe because it could be that the old primary decided something. So as a primary, my goal is to ask all of you, is anybody here locked? Right? And if I figure out I can wait for n minus f of you, and if I find that somebody is locked, I'm going to use that lock and try to repeat that value. Okay, so this is kind of the protocol. And again, the way that the replica will respond to this is it will respond if it's the same value that you're locked on, or if the lock is on a higher view than the view that you have. So questions on kind of how we maintain safety?
Can you maybe show an example of receiving a higher lock? Lock with a higher value?
Yeah. So let's assume that you received, so this is what happened in the world, and this is primary 1, and let's say there's primary 2, and primary 2 did a view change, didn't even see you, and it actually managed to commit. So here's a commit, and these nodes, there's like all these nodes. So this is committing on, let's say, x2, and this is committing on x, trying to commit on x1. And so there's one node here that's locked on x1, and let's say only one node here got a commit. And now you are the new primary. So you're primary number 3. So primary number 3 asks for different locks. In particular, it will see this lock, but let's say it also sees this old lock. Now this guy is honest. He was just late, so I couldn't, he was not part of this computation because he was slow. And so now the primary number 3 can convince this honest node that it's okay to use x2 even though it's locked on x1. Why? Because it has a proof, this lock is a proof that there are enough people that were willing to actually send the acknowledgement for x2, which means that there was no commit on x1. Okay, so that concludes kind of the safety. Let me kind of show you again how this works. So what do we want to do is we want to do this view change. So let's say we have a new primary, and here's primary 2. And basically, in order for primary 2 to start working, it has to receive all the locks from all the previous replicas. So in particular, all the replicas decide to send the locks to primary 2. So what does the primary do? Well, it looks at all the locks it receives, and it chooses the one with the highest view. And that's the one it uses in order to start sending, just like P1 sends a message X, P2 will send a message depending on the locks it receives. If it receives no lock, then it just sends whatever message it wants. If it receives some lock, it chooses the one with the highest view and uses that to send in this next round. And in particular, why is this live? It's because no matter what the honest people are locked on, if I hear from all the locks and I choose the maximum one, then everybody will accept it and will work with me. So I have enough people that will work with me. Right? So liveness depends on the fact that I received all the locks from all the non-faulty, honest participants. And so, the problem is that how do I know I received all the locks from all the honest participants? So I can definitely wait for n-f nodes here, n-f responses. If I wait for n-f responses, does it mean that I received it from all the honest participants? Yeah, it could be that the malicious are front running. They're sending me messages before the honest guys. Even if it's synchronous, right? Formally, I have to wait this delta time bound. Right? And this is kind of the challenge. And so, this is where you lose the property of optimistic responsiveness, in the sense that when you do a view change, you actually have to wait this delta time bound in order to make sure that you're receiving all the locks from everybody. Because if you don't receive the lock from everybody, you might choose a lower lock, and then there's this one honest replica that's not going to work with you because it thinks it's committed to something else, and so it's not going to continue with you. And since the malicious people are not going to work with you, now you don't have n-f people to work with you, and you're going to get stuck. So this is quite a pretty sophisticated attack. It's not something that will just happen randomly. It has to kind of have a malicious primary, send a lock to just one person, and this one person not be seen during the view change, and then it comes back to be seen. So it's not something that's going to happen every time, but at least in theory, it can. And this is kind of what the HotStuff protocol does. It basically removes this problem of a hidden lock. So this is here an example of a hidden lock where this one honest participant has a lock, and I don't hear this honest participant. So the idea in HotStuff is basically to remove this hidden lock problem by running one more round. So now that we're running one more round, what happens is I know that if any one of you has a lock, there's a large number of people that has kind of a precursor to this lock. Let's call this a key. Okay. So what is the advantage here? The advantage is that even if there's only one person that has a lock, so in HotStuff, this is, you can think about this round is called key. So we're adding one more round. So this is still not a lock. And then the next round we're sending is a lock message. So here's one poor replica that has a lock. What we're guaranteed is that there's a lot, n-2f honest participants that have a key. So when I'm doing a view change, when I'm a new primary, primary 2, that's receiving input from everybody, I might not hear from this poor one node that's missing that has a lock. But I'm guaranteed to hear from a lot of people that has the key for that lock. And I'm going to use that key to convince this honest node because I'm going to use that value. This is kind of the essence of the additional one round in HotStuff and how it solves the problem of the missing lock. And so what it means is that primary 2 can start working if it hears from n-f responses without waiting the whole delta time. And so what it gives you is the ability to kind of work at the network speed. So in particular, if messages arrive very quickly, but my time bound, let's say, is 2 seconds, let's say after 200 milliseconds I receive M-ISF messages, this protocol says that you can continue working, and you're guaranteed liveness even if you're just waiting for M-ISF messages. So when is it very important? It's important when there's kind of a big gap between your worst case assumption on network delay and the actual assumptions on network delay. And so this is kind of the notion of optimistic responsiveness. It's a protocol that makes progress at the speed of the network. So if the network works very quickly, let's say small delta, then your protocol progresses as a function of small delta and doesn't have to stop in these big delta timeouts. Any questions here about liveness?
The guy with the single guy with the lock, he will eventually have to participate in the protocol. We're waiting for him to participate, but you can then convince him with the key.
With one key. So what's guaranteed is that my view change will hit at least one key. And so with just one key, I would assume his value. So basically, when I see when I see this key, I will use his value, and since his value is the maximum one, everybody will be willing to work with me. So here's so we're almost done. So here's an attempt to do the basic protocol without this one extra round of key in one slide. So we're actually starting from this view change phase. So here's the primary, and everybody is sending messages to the primary. In particular, they're sending the highest lock that they have. And what the primary does, it actually has to now decide what it's going to send. So if nobody is locked, the primary can just choose whatever value it wants. But if the primary is locked, then it has to, if the primary receives a lock, then it chooses the lock with the highest view and uses that value and sends that along with that lock in order to convince people that this is kind of something that they should use. So this is the phase that we've already seen, the send phase. And the only difference, as you can see, is that you're either sending something without a previous lock or sending something with a lock, which is the highest lock that you've seen. So this is the send phase. And the same thing happens after the send. A replica sends back an acknowledgement. But now, the important thing is that, I don't send the acknowledgement if I'm locked on a higher view, or if the value is different than the value I'm locked on. Okay, so previously we just said, if Roman sends a message, we just sign it, the first one. But now Roman sends a message and he gives us some lock from some previous view. Okay, so let's say we're in view 100 and Roman sends a message that contains a lock from view 50. If I'm locked on something in view 20, I accept this message because 50 is bigger than 20. But if I'm locked on view 70, then I ignore your message because I'm saying you're sending me a proof of something that you're in round 100 sending me something that happened in round 50. I've seen a lock in round 70. So I'm scared that in round 70 there was a commit. I'm going to ignore you because you might be malicious.
Why can't they just like in theory falsify the lock?
Yeah, perfect. So because every time you send this lock, so here's a lock. The way you receive this lock is it contains n-f signatures. So basically, either it's an accumulator or a threshold signature, so BLS multisig, where the lock itself contains all these signatures, right? So there's a cryptographic proof that this is a real lock. I can't falsify it, but it's a great question.
So does this mean if Roman went down, then the system would never become available again? He was down permanently because the primary would be waiting indefinitely for the last response? Like if it has to wait, well, I guess for wait, how does it wait for the entire delta? I'm trying to say, like, this is without optimistic response.
Yeah, so without optimistic response, let's say what Casper or Tendermint is doing. They basically, assume that these messages have a bounded delay, and there's kind of, a proof of work system that's ticking, and well, you're supposed to wait a minute, or let's say 10 minutes, I think or 5 minutes is the Casper timeout. You wait 5 minutes, and they actually want it to happen every 5 minutes. They don't want it to happen faster. They want this finality. So, in some use cases, it makes sense to say every 5 minutes, I'm going to wait to hear everybody. Yeah, and this liveness attack is actually quite sneaky. In the usual case, this won't happen, right? So it's actually, you have to really try hard to create that liveness attack. So yeah, after you receive an ACK, you send a lock, and after you receive this lock, you respond with a lock acknowledgement, and then you send a commit message. And so the moral of the story is that you thought you'd come here to see these fancy, complicated Byzantine agreement protocols, but everybody's sending a message. You send it back. So you see this accordion type approach. It's very nice because it's simple. You can pipeline it, so you can replace the primaries every round. You can put multiple copies of this protocol, and so it has kind of very nice aesthetics that allow you to optimize various parts of it. But really, before we go into optimization, you really need to think about kind of what does this protocol look like. So at the end of this commit message, what are we doing? Well, we're sending a view change to the next primary, right? So we can kind of just continue. And so you can see why it's a linear protocol. This particular protocol is not responsive because when you're doing a view change, you have to make sure you hear all the primaries, all the locks. Yeah, so I just want to say that if you're rotating leaders all the time, then we're still not done here because you kind of have to know who is the primary. And so you have to keep track, right? In particular, if the primary is changing every 5 minutes, then you can just look at your clock and see who's supposed to be the primary, or at least look at some deterministic function of the time and so on. But here, if it's changing very rapidly, then you have to kind of follow the primary. So there's this kind of problem of Byzantine view synchronization, and some new results about how to do this efficiently. And the other problem is, well, if there's a primary and we know who the primary is, the adversary also knows who the primary is, and the adversary is going to launch a denial of service attack on that. And so the approach is to kind of use randomization, and even if you use randomization, well, okay, you have a surprise primary, but then we go and attack it after we figure out who this primary is. And so this more complicated approach is basically to hide the primary. And so the way you could hide the primary is by having everybody act as if they were the primary, and only in hindsight you elect one guy to be the actual primary, and everybody else is actually a decoy. So this really gives the adversary a hard time because it can't guess who was the real primary and who's the decoy. Right? This gives you kind of adaptive security. All right, so this is kind of my conclusion. Again, 3 parts. The first was focusing on Bitcoin, and at least how distributed computing sees Bitcoin and Nakamoto consensus as a major breakthrough in this area. In particular, providing a synchronous Byzantine agreement protocol that doesn't require a PKI and obtains this optimal bounds in terms of threat of security. We then talked about kind of the state machine replication approach, and we went over kind of the older history and also the new modern approaches, and kind of split it into the asynchronous protocol, synchronous, and partial synchrony. And finally, we did kind of a very brief overview of how these HotStuff protocols look like. And you can see on the one hand, they look very simple. On the other hand, there are these small nuances about when are you allowed or not allowed to sign, and you actually have to make sure that when you build these systems, you're not making mistakes doing that. So this is how I'm concluding. Thank you, and I'm going to take a few questions. That's it. Thanks. So we have one more of these. Somebody wants questions.
I have it.
Okay.
Maybe a small question about VMware activity at the blockchain space. If you can share with us what you as a company are doing in the space, or what you're researching.
Yeah, sure.
Your business approach and stuff like this.
Yeah. So at a high level, VMware provides infrastructure for IT. So we provide compute infrastructure, storage infrastructure, and network infrastructure. And what we believe is that in the future, this notion of trust is going to be a part of the compute infrastructure that people will want. And so VMware will be in the business of providing trust infrastructure. We believe that privacy is another type of infrastructure that people will be interested in, and we'll provide privacy infrastructure as well. So there's an open source project, Concord BFT, that you can look at. If you Google VMware blockchain, you will find that there's kind of an announcement with ASX. This is the Australian Stock Exchange. So that's kind of one of the public projects that I can speak of. You can Google that. All right. Thank you.
Thank you.